a minute. As you guys are your revision. So yeah, since regression is a type of a model, whenever you are having the target column continuous in nature, then you are going to use regression or supervised machine learning. In that section, you are going to choose regression type of a model. Understand that we are right now dealing with the supervised machine learning, okay? Once unsupervised will come into the picture, I'll let you know. So as I told you that how your regression model is going to learn, okay? Since regression model has its own way of learning, but there is one concept of regression model called as linear regression, okay? So what is linear regression? Linear regression completely works on the equation of line, where we are going to have one independent feature, or there is a possibility that we can have n number of independent features that will help me to predict the dependent feature. Understand that your output is always going to be dependent upon your input, okay? Which means to judge your output y, you will be needing variable x every time, okay? Which means these variables are independent amongst each other, but the combination of these independent variables will help me to judge the output y. So we can call the output y the dependent variable. Okay. As I told you that this equation, or let's say this regression, completely works on the equation of line, which is nothing but y equals to mx plus c. Here y equals to mx plus c. Do not forget that your y is again nothing but your target column. Just a second. Y is nothing but your target column. Okay. M is nothing but the coefficient, and x is nothing but your column or independent feature, okay? Whereas C is nothing but the error, okay? So consider that you are going to have some coefficient associated with that column along with some error that will help you to predict the column 1, okay? Now, let me tell you one thing honestly, since this is the regression type of a model, everybody knows that prediction of such kind of values gets difficult because it is very variable in nature, and the pattern is getting changed every time or for every entry. Okay. So previously we were talking about the linear regression. Since as I told you that we cannot apply the linear regression on the nonlinear data. So what is my first job? To check the linearity. If any of my input column is following or creating a linear relationship with my output or target feature. Okay. Any of them. Suppose if you are choosing simple linear regression, so first you have to check the linearity of the data set. If it is forming a straight line, then well and good. If it is not forming a straight line, which means it is not even showing a close relationship of linearity amongst each other, which means it is of no use. We cannot apply linear regression model on that particular data set. Okay. So always understand there should be relationship between x and y, which is linear in nature in the case of simple linear regression. In multiple linear regression, any of the input columns should create the linear relationship with the target feature. Any of them. Okay. It's not necessary that every column should make linear relationship. Any one of the column can make or is going to make the linear relationship with my target feature. Okay. So just to create or just to talk about linear regression, this is the first checkpoint. Okay. Now, we were talking about this simple linear regression, and we are going to implement this model today itself. Okay. Now, let's quickly go through the definition of this. Using relationship between variables to find the best fit line or the regression equation that can be used to make the predictions. Okay. Today, I'll show you by creating how your best fit line is going to look. Okay. And it is time to tell you that we are going to choose regression equation, which is nothing but the equation of line to make the predictions. Okay. If we only have one variable, then mean is the best way to predict. Here you can see that y is equals to b0 plus b1x, where b1 is equals to 0 because mean is the best fit line. Mean is the best fit. b0 is equals to 0. What it is trying to say, guys. Look into this. What we can say, the screen. here you can see we are having two columns, okay? We are having the column number 1 as some number and second is the tip amount, okay? Customer consider. If you are having one customer, the tip amount is 5, two customers, 17, 3, 11, 10 of that, okay? Now what it is trying to say, when you are having one variable in your linear regression model, the best fit line, or let's say the best way of doing the prediction is with the help of simple. Instead of doing a lot of tangent, what you can simply do is simply write or find the mean of that column and you will be able to make the prediction. Okay, so what it is trying to say, suppose if you are having the 7th entry here and you want to predict the 7th entry, you can predict it by calculating the mean. But we are not going to go with that way. Okay, we are going to apply the simple linear regression specifically and we'll see what the changes are going to be looking like. Okay, because here you can see guys, the best fit line, what is it is coming like a straight line. It is not showing a linear relationship, so the data is also not linear. So we have to keep such things in mind. Okay, simple linear regression. Now bivariate, two variable. Okay, now let's talk about, this is something very important, two variable statistics. The best fit line will always pass from centroid. This we will talk about later. What is centroid? When we are going to deal with multiple linear regression. Okay, one dependent and one independent variable is going to come into the picture. Simple. And the equation of line b0 plus b1x. Here the value of 0 is not equals to 0. Leave it. Okay. First we will try to solve the model and then we'll come back to understand such things. Unless it is going to create issues in your head. Okay. Cost function already came. Leave it. Look into this. This is something important. Okay. Linear regression. You can see we are having 3 types of linear regression. Okay. Since you decided that your dataset supports supervised machine learning, inside the supervised machine learning, you choose regression. Now, what kind of regression you are going to impose on the dataset? We have simple linear regression where one dependent and one independent feature is going to come into the picture. Multiple linear regression where multiple independent feature and one dependent feature is going to come into the picture. Polynomial linear regression when we are having multiple independent features but it is creating a polynomial equation. Guys, do you understand what is polynomial equation? When you are having column number 1, x1, it is nothing but x to the power something 1. Okay. Here it is x to the power 0. Here it is x to the power 2. Likewise, it is going to go increase x to the power 3, x to the power 4 till x to the power n, describing where n is equals to number of features. Okay. So we'll see all of these 3 regressions one by one, how to find their cost function, how to find their error rate and how to reduce errors as well. Okay. Now, since we were talking about the error, what I told you guys, how we can identify the error? Because in the previous situation, what I told you, error is nothing but original minus predicted value or predicted minus original value. You can judge it with any way. Okay. So what was the situation coming into the picture? We were getting the answer as 0, which means my model does not contain any sort of error. Is it a true case, guys? That my model does not have any sort of error? No. My model does have some sort of error, right? So how we can judge the error of linear regression model? Do you guys remember? How we can judge the error of linear regression model? Any idea? What the concept called as? Nobody? Original minus calculated, that is correct. But if you guys remember, let me revise you the concept. I think you guys have forgot. Here you can see these dots are the original data points. You can see we are having x and y, right? X is 2, y is 2. We are having the data point coming somewhere here. X is 3, y is 12. Somewhere here. X is 5, y is 11. Okay, somewhat like this. We are having original data points already plotted. Now you can see what is this straight line? This is the best fit line. How this best fit line is going to come? With the equation y is equals to mx plus c. Here can I write simply that mx plus c, where x is nothing but this feature. X is going to be some coefficient which will tell me the importance of having this feature, and c is nothing but the error rate. This will help me to plot the best fit line. Okay. Now my best fit line is the predicted line or predicted data points. My rest of the data points are somewhere far from my predicted data points. Understand that we deal with the regression model with the help of equation of line. So all of your predicted value will fall within a straight line. Okay. Now what is our task? Our task is to judge that my predicted value is how far from my original value. As I told you that since it is a regression model, we cannot judge or predict the exact value. Getting my point? Suppose this is the point 2, 2, right? Or let's say this is 100. I cannot predict exact 100, guys, because the pattern is continuous in nature. It is getting changed for every next row, right? Since the prediction of such type of values gets difficult, so we decided to create a best fit line and to judge. What is the best fit line? Best fit line will say that I am going to cover most of the data points which are original to the nearest. There is a possibility some of them might overlap to this point or this line. Okay, since I am having some of my original data points, this is my best fit line. What is my job? To calculate error, because I can see that the prediction is somewhere near far from my actual or original value. How am I going to predict error? Here you can see 2 minus 6 is somewhere going to be minus 2 since it is going below the best fit line. So you can say that calculated minus original or original minus calculated, whatever it is. Okay. Now somewhere here you will also see this is 1 plus 1, and here also somewhere it is going to be plus 1. Okay. So we are having 2 plus 1s, 1 minus 2. If I am going to find the average error, will these not be cancelled out? Of course it is. There is a possibility that most of the errors will cancel out on its own. Yeah. So there is a possibility that most of my errors might get cancelled out. Okay. So then we will get stuck here. How we are going to find error then? If there are chances that most of my errors have a possibility to get cancelled out, how am I going to judge the error? Then the concept comes into the picture. Try to neutralize this negative value. Do some mathematical implementation on this error value so that this negative or this minus will get removed. So if you guys have idea, or let's say if you guys were good in mathematics, if you remember, we have two situations. Either you can apply modulus in front of it, right? What is mod? Mod converts every negative value into the positive one. Okay? And you can either square this value up. Okay? You can do both of them. So, if I am going to use a mod in front of this value, it will make this as positive 2. These two are already positive. If I am going to find the average error of this model, it will give me the error somewhat like this. Average error. No issues. Nothing is getting cancelled out. Best part. The another way is to square this error. Okay, and in other terms, we call this as tweaking, or let's say channelizing this error. What I'm doing, I'm squaring the error. Okay, so what will happen? I'm going to do square of -2. Here, these are the already positive one, no issues. So basically what will happen? This will become +4, this will become +1, and now I can find the error like this as well. So when I find the error with the help of modulus, I am going to call that as mean absolute error. When I find the error with the help of squaring the terms, I am going to call that as mean square error. Okay. Now there is one question for you guys. Which type of error between these two? Okay, root mean square, we'll deal with it later. Right now, look into the screen and we have two types of error. Mean absolute error, which is just changing the sign to positive, and mean square error, which is changing the sign to positive by squaring it. Okay, which one is the best for the outlier? What do you guys think? If I have the outlier in my data set, which type of error will easily help me to identify or judge the outlier? What do you guys say? Outlier or noise? You can call it whatever you want to. Suppose we are having one value coming somewhere here. Okay? Okay, not here, let's say here. Okay? Completely away from rest of the values, very far from the best fit line, which will help me to do the better judgment of that point. What do you guys think? Socho. Okay. Think, guys, basic mathematics you need to understand. Can't think? Correct. Okay. Those who have written MSc or squaring one is the correct answer. Do you understand we are having a distance which is very huge, right? If I'm squaring the distance, which means I am defining that rest of my data points or squares are coming very near to my best fit line, whereas this outlier data point or this squaring of this data point is telling me that we are having more noise in this data point. Getting it? Squaring is nothing but help me to judge this particular data point is very noisy and away from rest of the data point and causing me big or huge error. Based on that, we will decide either to keep this data point or to remove it. So mean square error is very helpful or very good with outlier type of data. Then you are having the data set and you can see once you draw best fit line and once you draw the, let's say, once you draw the original data points at the best fit line. Now is the time, because you are having three different type of error judgments, right? Mean absolute, mean square, and root mean square. Now the question arises which error you are going to choose for your model. You cannot move forward with all three, right? You have to select one metric to move forward with. So whenever you are having the outlier or more noise in your data set, mean square error is the best choice. Okay. Whenever you can see there is hardly some differences in your data point, you can choose mean absolute error. Okay. Now you can see every data point is enough far from the line. The good choice is root mean square. Okay. RMSE. So root mean square is nothing but root over mean square error. Simple. Getting the point? Let me repeat it once again. Whenever you can see that you are having some outliers in your data set, go forward with mean square error. Okay. When you see your data point are much too close with your line, best fit line, you can go forward with mean absolute error. Okay. But when you can see there is a best fit line and most of the data points are far from your best fit line, go with the root mean square error. Okay. Root mean square error is nothing but root over mean square error. Simple. You cannot move forward with all three, right? You have to select one metric to move forward with. So whenever you are having the outlier or more noise in your data set, mean square error is the best choice. Okay. Whenever you can see there is hardly some differences in your data point, you can choose mean absolute error. Okay. Now you can see every data point is enough far from the line. The good choice is root mean square. Okay, RMSE. So root mean square is nothing but root over mean square error. Simple. Getting the point? Let me repeat it once again. Whenever you can see that you are having some outliers in your data set, go forward with mean square error. Okay. When you see your data point are much too close with your line, best fit line, you can go forward with mean absolute error. Okay. But when you can see there is a best fit line and most of the data points are far from your best fit line, go with the root mean square error. Okay. Root mean square error is nothing but root over mean square error. Simple. Let me write down. So since guys, we are having three types of error. Mean absolute error, which works with the modulus. Okay. Which means I'm going to apply modulus in front of my error, convert the negative number into the positive form. Now the another one is mean square error, which means I am going to square my error term so that I can convert the negative one into the positive one by squaring it within the same number. Now the third one is nothing but root mean square error, or we call that as RMSE, is nothing but square of your, root over mean square. Simple. The error which you are finding here, we are just applying the root over y to normalize it. Suppose I don't want the tweaked error. Getting it? Because when we have outlier, I choose mean square error, right? Just if we are having noise in the data set, the noise will get more noisy and it will help us to judge those data points. Since we are not having that much noise, so I can move forward with root mean square. What will happen? You are going to find the mean square error. Simply do the root over of the mean square error. You will find one value. It is the normalized error. Simple. Not the tweaked one, not the squared one. Normalized one. You guys know, right? If you are doing square of -2, it is nothing but 4. But later you want to know the original error value, what you can do? You can square, you can apply the root over to the 4. That will give you the original error value. So we are doing this way for mean square. We are doing this way for root mean square. Getting it? Any more questions, guys? Sure. Let me give you a data set in which we are going to apply simple linear regression. Since you are guys going to find it on your own, that will help us to understand the models a bit better. What about the girls? I can see the people who are very active in the starts, they are not speaking right now. Don't go blank, guys. Just wait a minute. Let me share the data set with you. Company profit pattern. Tomorrow I will upload the notes also in the drive. Okay. So whenever you get time, please go through the notes. And if anybody of you is free, if I forgot to upload the notes, please do remind me in the group as well. Okay. This is a company profit data set in which we are going to work. Since it is not a case study, guys, simple implementation of the model on the data set. Case study, we are going to do from tomorrow. Okay. So we'll find root mean square error, everything. We'll also draw the best fit line. Let me just open the Jupyter notebook. Meanwhile, I'm suggesting you guys, those who already have open Jupyter notebook, please read the data set. Do not forget the concept of train test model is still sticking. Okay, we are again going to train it. We are again going to test it. Again, the X and Y distribution is going to happen. The previous concept is intact. We are just changing the model. Okay. So you can say that your machine is getting changed, but your product is similar. Okay. Previously, you were having the LG washing machine. Now you're choosing the Samsung one. But you are having the similar clothes. Oh God, why does this slow? Just checking. I'm naming the file as simple linear regression. Okay. Let's read the data set. Simply writing import pandas as PV. The basic data set reading as it is CSV file. So I'm writing read CSV, mentioning the path of the file. The name of the file. Okay. Have you read the data set? It's done. I'm saving that in here. Please give me a quick confirmation once it's done. Okay. Okay. Already received one confirmation. What about rest of the people? Guys, please do apply the models with me so that you will get the idea that where you are getting stuck. Okay. Okay. Now look into the screen. You can see this is a data set. Okay. Now data set consists of startup year operation and the profit. Basically, we are having some data of some company, and you can see the data set is a bit small. Just a second, guys. It is very small. Okay, we are doing simple linear regression, right? It's fine. Yes. Good, no issues. Since it is simple linear regression, that's why we are choosing this small data set, okay? Once we will move forward with multiple linear regression, I'll show you. This is just for the practice, understand that, okay? So we are having some startup year of operations like this, and we are having some profit like this, okay? Why I am choosing the small data set, guys? Just to show you. Since it is only 30 entry, I can show you by drawing the best fit line. I can show you the original data points and we can actually judge the error. So this is deliberate, okay? This is startup year of operations, which means how many number of years, or let's say from how many number of years this company is operational and how much profit it is making, okay? You can consider the profit in thousands, okay? So 38143 thousands, 45452 thousands, okay? We are having two columns. Now, what is the case here? As I told you, it is not something related to the case study. It's just based on the numbers of year the startup company is operating, we have to judge the profit. Okay. So we easily understand that the column or the target column here is the profit and startup year operation is the input column, which is independent in nature, and the profit column is the dependent one. Very basic. Okay. Sure. Since we are done reading the data set, let's distribute x and y, which is very easy as well. So I am going to choose x is equals to df dot ilog. I want all the rows, but I want only first column. Okay. So can I write something like this? Starting index position from 0, ending index position -1, which means by default it is going to pick this one only. Startup years of operation. Okay. And guys, why do we write dot values? Let me show you. You can see if I'm going to write X, it is looking like a data frame. Okay. We have to convert this into NumPy array, guys. We cannot run the machine learning model on the data frame. We want arrays. That's why we write dot values and this will get converted into array. So that I can feed this array inside the model so that my model can predict. Okay. Similarly, I'm writing this for Y. Y equals to df dot ilogs. If I am going to be in your place, if I were you, how I'm going to write it? So it is going to be my approach, somewhat like this. Okay. See why? You can see it is giving you the error somewhat like this. But as you can see, the dimension is getting changed, right? It is coming in the one-dimensional format. So I can write the starting index position as 1, ending index position as 2. That is going to be two-dimensional in nature. Okay. Also, instead of choosing df of ilog, you guys can also select something like this. You just need to select the profit column, right? you can select like this as well. No issues. It's not necessary that every time you have to like write iLog. You can write somewhat like this as well. Okay. So both of the things are correct. Since I choose this one, basically, why? Because this gives me the idea that it is getting converted into array. Okay, so I want to be specific. So these two are the distribution of x and y. Simple. Okay. Now, once the distribution of input and target is done, what is the next thing which we need to do? We need to train, test, split the model. And the, or you can say, the code or the command for doing the train, test, split is similar as that of your k-nearest neighbor. There is no difference. Okay. So simply you can write from sklearn dot model selection. Okay, let me check it. Drop your command in the chat box. Look it up. Model selection, import, train, test, split. Okay, df.iLog. You are printing x. If you want to see the values, you have to write x as well, like this. Then only you'll be able to see the values.
Okay.
Okay. Okay. So train, test, split. Now again, the distribution is x train, x test, y train, y test equals to train, test, split. Inside that, you have to give your x and y, which means your input and the target features. So x is my input feature, y is my target feature, and we find the test size here as 0.3, and I am choosing the random state. So I am fixing the random here itself. State as something as 2. Okay. So this is your x train. Okay. Suppose I'm not choosing values here. Okay. We'll do that later. Just to show you the index position. Okay. This is your x train. Now you want to see the y train, how it is looking like. You can see the same indexes are coming. Okay. So that is why we write xy here, so that the alignment of the randomness should remain intact. Okay. So do this, guys. I hope nobody have any sort of question at what I have written here, because train, test, split is nothing but the model which you have imported. Now xy is nothing but your input and target column or data set. Now test size is telling you that 30% of the data will go for the testing purpose, and by default it will understand that the train size is going to be 0.7. So guys, you can mention either of them. Either you can mention test size or you can mention train size. Okay, we just need to remove test from here and write train. Okay, no issue. But basically we choose test size to be there. That the testing part we are giving as 0.3 or 30%. Now random state is equals to 2 or any number, whatever you want to get, just to fix the randomness of the data. Okay. From sklearn dot linear model. Guys, this line is going to get changed along with the models, which means if you are going to have k-nearest neighbors, so you have to choose n neighbors. Okay, here we are talking about the linear regression model, so you have to choose linear model. So from sklearn dot linear model, import linear regression. Okay. Now understand that I am importing linear regression model. Okay. Now, if you guys remember, we have multiple linear regression models. Okay. We have simple linear regression, we have multiple, we have polynomial. So which one we are picking right now? Okay. We are not sure about it. Either it is going to pick simple linear, either it is going to pick multiple or polynomial. So let me tell you one thing, that this sklearn is smart enough to understand if you're going to give only two features, it will understand that this is nothing but the simple linear. If you're going to give multiple features, it will again understand that it is multiple linear. Now, by the end, if it is going to give you something called as, let's say, polynomial kind of equation is coming into the picture, it will understand it is polynomial linear equation. Okay. But one thing we forgot, guys, we forgot to check if it is following some linear relationship, which means my x and y is following some linear relationship or not. Okay. We'll see that later. We'll plot the graph with df of years of startup and year of profit, and we'll see if it is following a linear relationship or not. Okay. Chalo. We imported linear regression. I am choosing one variable called as linear model. I am, let's say, linear underscore 1, something which is not identical to this one. So linear underscore is my variable name. I am choosing my linear regression model here. And simply, I am again going to call this model and mention the values. We can either mention here, but I'm just keeping it like this. Now we have to mention what? X train and Y train. We are training the model as of now. Simply we are going to mention X train and Y train, which means, okay, dot fit, I forgot to mention. Okay, linear regression. Wait a minute. I have to choose this variable. Sorry, guys. Okay. So what I have done, I stored the method in this variable. Once my model is done learning the pattern, what is the next thing? We have to check the model score. Okay. So we'll check the score later. Let's check the prediction first. So simply I'm going to write ypred equals to linear underscore 1 dot predict. Now it is going to do the prediction, and inside the prediction we always give x test. So it is going to take x test as the input and going to predict the ypred. Now we already have y test with us, from which we are going to cross verify that what is the y prediction, what is the y test, and how the values are getting differed in these two variables. Okay, so if you want to check, let me run this. I'll show you how my ypred is looking like. Okay, and how my y test is looking like. Can you see that? I am telling you one thing very honestly. You will find that no data point is going to get matched. There is a possibility by point they are going to vary. Isn't it? So yes, in classification, we get exact yes, we get exact no. But in the case of regression, there is no such case. You will see that your prediction is always going to be different from your original value. Either by point, let's say it is 45452. If your model is performing very good, again it is going to predict 45452.01, something like this. Okay, so either it might go up or down in the prediction, but never find the exact value. Okay, so we have ypred and y-test value somewhat like this. Yes, so if you guys have any sort of question, you can let me know. Till here we are good. Okay, let me give you a moment. If you guys are jotting it down. Okay, X train is not defined. Make sure you have written this particular line. Or if you have written, then you have ran it or not. You might forgot to run this line, that's fine. Yes, we are going to plot the graph. The next step is plotting the graph only. Okay, let's move forward. Now, what is the next thing? We have to judge the score, right? How accurate my model turned out to be. So for linear model, we have this method called as, it is inbuilt here. We don't need to import some metric or something. Simply write linear model dot score, and inside that give X train and sorry. Oh my god, it should be linear. Linear underscore 1. That is where I have stored. Oh, wait, guys. I discovered perfect. Okay, so after your model learned, you guys know it created a best fit line for your original value, then it created a best fit line, just the predicted value. What is my model score coming here out to be? Somewhere near to 88.8%. Okay. After learning the model, that's why we are judging it with X test and Y test. Okay. Because we are judging the model score, the training scale. Okay. For the prediction or for the error, we are going to move towards the error direction. This is just the model score. How accurately it is judging or how my linear model is working with. And understand that we never judge the performance of regression model with the help of accuracy. Okay? We always judge the performance of a linear model with the help of error. Don't forget this point. In the case of classification, yes, we do find the accuracy and it always comes near to the precise mark. But here, understand that, yes, it is telling you that your model is 88.8% accurate, but accurate in the sense of nothing, like it is predicting the value as it is. No, near about. It is predicting your value near about. Okay? So, it is predicting your data point to the original data point near about to 88.8% accurate. Do you guys understand that these two values are never going to get matched? Y test or Y pred? Suppose if I give Y test here and I'm giving Y pred here. You can see what it is giving me the answer as. The linear score is somewhere going 9390544, making no sense. Why? Because what I told you, if you guys remember, once we started the linear regression, you guys remember what happened? I told you that this is your X column, this is your Y column, and it is plotting the data points somewhere like this, right? And from there, here we are going to draw one best fit line. Okay? Now, the accuracy which we are judging right now with the help of X train and Y train is telling me that how closely my data points are going or my data points are coming from best fit line. So this is your best fit line. This X train and Y train is telling you these points. Okay? And the linear score or the accuracy is getting judged on the basis of this point. Can you see it is coming something different? If I'm going to run this again, wait a minute. I disturbed the data set. It should not come 96. I'll be choosing the random state, guys. Wait. No, we are talking about training value, not test. What your accuracy is coming? No. Chalo, if you want, let me give you X test and Y test. Okay? You can see. Now, if I'm going to give X train and Y train, don't forget, guys, this is linear regression model. This is not a classification model. Okay? So basically, if you are going to run this, maybe train test got shuffled. I'll do some disruption in the data set. That's why. Wait a minute. So basically, in the classification, it was easy for us to judge how to calculate the accuracy. We were checking the predicted, we were checking the actual value, right? That was giving me the accuracy of the model. But here, do not forget that how we are judging the score of linearity here. Okay? The linearity of score is getting judged with your X train and Y train, which means your data points are getting plotted here, and linear score, which means a best fit line, is telling you that how near your data points are. Okay? So basically, it is giving you the accuracy by calculating the error. Getting it? So this 96.26, whatever accuracy is coming on the basis of X train or Y train data points getting plotted with the help of best fit line. Am I making sense? Because if you guys are going to write Y pred and Y test, not going to work. Why? Because this is your Y prediction, this is your Y test. If you're going to plot the graph, best fit line is not going from here. Best fit line is for training data set right now. Wait for a minute. Let me plot the graph and then we'll talk about this. That why I am choosing here the X train and Y train. For whenever we talk about regression model, guys, this is how it is going to give you the score. Okay, this is the score of linearity. And this is not actually how we judge the performance of a model with. We judge the performance of the model with the help of error. Okay, we try to reduce the error because your regression models are never going to get accurate. You can see that. If I'm going to run this again, your error will come, your accuracy will come something different. Because you can see these data points are never going to get matched. Okay, coming back to the point, let's visualize it. Then I'll come back to this point to explain you guys that perhaps choose an X train and Y train. Okay, let's just do the visualization. Okay, so the first graph which we are going to create is, okay, accuracy is coming fine. Should come somewhat like this. So this is what we are going to plot with the help of C1 and matplotlib. So let's choose matplotlib. Import matplotlib dot pyplot as PLT. Okay. Now PLT dot scatter. Inside that, I am giving the training data set of X and training data set of Y. I'm choosing the color to be red. Simple. What I'm doing, guys, I'm plotting the data points where my X train and Y train is getting collided. If you guys remember the graph number 1 in the PPT, okay, this graph we are plotting. You can see the data points. Okay, so this graph we are plotting as of now. That's why we are writing X train and Y train. I'm choosing the color to be red. Okay, let's just run it. You can see my data set is linear in nature. I can see with the help of these data points. Well and good. Now let's try to create a line here. Okay, for the X train. So how I'm going to do that? Simply I'm writing PLT dot plot. Inside that, I am mentioning X train and I am mentioning linear underscore 1, which is nothing but my model, dot predict, it's true. Okay, this is what it is going to do the prediction of. As of now, I'm going to show you the best fit line. So let's make the color of this as green and let's try to run this. Now I can see this is from where your best fit line is going. So this is your X-train data. It predicted the best fit line for the X-train data. And this is how your graph is looking like. Okay, this is point number 1. Now point number 2, we are going to do the same thing for the test. Okay, to see if the test is working properly or not. Just a second. Now we'll create the testing graph. Sorry. So simply I am writing plt dot scatter. Okay. Now you need to understand one thing. Now we are going to plot the graph of the predicted one. Okay. This is, so already you can see this is the X-train and these are the predicted value for the X-train coming within this best fit line. Okay. Now we have to check for the Y train or Y test, how my test value is behaving. Okay. So for that purpose, I am simply choosing one variable, let's say X of serial. Wait for a minute, don't hurry. List of range of Y pred plus 1. Okay. This will help me to choose my x-axis and y-axis is going to be my y predicted. I am simply drawing the color here as blue. Okay. Length. List of range. Let's start that from 1. Then length of y pred will give me the value. And parenthesis maybe. Okay. Now you can see the data points. What is happening here? You created a range. Okay. Starting from 1. Length is nothing but the length of y prediction. What is the length of y prediction? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So why we have done just for the x-axis, so that I can draw the x-axis here and I can plot the y predicted values. You can see these are the predicted values. Okay. Now I am going to show the y pred and y test comparison. Similarly, we have done that above. So I'm simply writing plt dot scatter once again. My x of serial, just to keep the x-axis intact, and I'm choosing y-axis as my y test. I'm writing the color here as, let's say, green. Can you see that? How my predicted value is getting overlapped with my original value, but some of my predicted values are far from each other. Getting it? Now, keep one thing in your mind. Can I find the accuracy from here? Can you see? Is it possible? Because the data points are very small. Getting it? The length is very small. So finding accuracy from here, I don't think so will give me any sort of chance, because I cannot see the best fit line also going from here. You can plot the best fit line from here only, or for this type of data, which is for coming for the X-train or Y-train. Getting the point? If you guys remember, let's go back to the PPT. X and Y-axis were there. We were plotting the graph for this and we were drawing the best fit line for this data set only, right? And from here, we are going to judge the accuracy or error. That is what happening here as well. Now, is this making sense? That why are we choosing X-train and Y-train here to judge the accuracy? What say, guys? choose some different color. Okay. Am I making sense or am I just blabbering? Let me give the title to the graph so that you guys do not forget this. Bolo, what happened? Go to dot title. Change set graph. Okay. To give the title here as test set graph. Okay, now we'll see the comparison actually. How the comparison is looking like. Yes, guys, are we together? Any questions? I think you guys are blown. Just remember one thing. Whenever you want to judge the linear score or the score of a model in linear regression, we usually choose extreme and White-Ring. Okay? Why? You can choose any other combination, you will never find the accuracy to be coming like this. What is the reason? Because guys, if I'm going to choose Y-test and Y-pred, how it is going to identify the accuracy? Because there is not something called as best fit line we can draw for it. The data set is so small that the creation of best fit line will get difficult. Usually we create best fit line while model is getting trained, right? So my model was getting trained, I created the best fit line and I understood that how far the data points are going based on the patterns. And that is why I try and judge the accuracy somewhere from here. It is okay, Subhashri. If you guys are getting the points like this, it's okay because there is a possibility the data set is getting randomized, right? Some random entry is going in the train, some random entry is going in the test. There is a possibility that your graph might look different from me, and that is okay. No issues. Okay? There is not a necessity that exact same data points for me, which is going for the test part, is coming here, will be same for you. Okay? Now the last graph is going to do the comparison. It is the best graph. Let me show you. I'm simply choosing plt.scatter. We are going to do the comparison, okay? And this is going to be X test and Y test. And I am going to choose the color as red. Okay, this is your test data set. Now I am going to choose the prediction data set. plt.scatter your X test and your Y red. So based on the test data point, what is your actual data point looking like and what is the predicted data point looking like? I'm changing the color here to blue. With free mind, if you guys understand this tomorrow, you can see. Is this making sense? X test, Y test. These are your original data points. X test, Y pred. This is your predicted data points. Getting it? I cannot plot the graph for Y test and Y pred. That's why I have written here something called as extreme White-Ring. The combination of XY will come into the picture here for the judgment of accuracy. Okay? Because this is continuous type of a data, guys. We cannot do the judgment basis on the Y-pred or Y-test. Okay? And if you want to see the best fit line for this, simply you can use this thing. Okay? You are write down instead of Y-pred, paste it down. Instead of scatter, choose plot. Instead of extreme, write expressed. Okay. So instead of showing the data points, it is showing you the desperate line. Simple. But do not forget, again, I am choosing X test here and Y prediction here. Okay. This is nothing but the Y pred. That is what we have stored, right? If you guys remember, you can see. Okay. So either you can write this or you can write Y pred. Whatever. It's just change this to plt.plot instead of scatter. So it will give you the best fit line for this as well. Okay. And based on this, the accuracy is getting judged.